Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to talk about how to control for fixed effects and seasonality in analysis with macro marketing data. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. This lecture is divided into three parts. In the first part, I'm going to first introduce fixed effects and how to handle the fixed effects in real data by using dummy variables. Handling fixed effects is sometimes very important in analysis because omitting the fixed effects can lead to a large bias in the estimate of other effects. This bias is called omitted variable bias, and I will explain what it is and why it appears. Then, I will explain how to use the concept of the fixed effects and dummy variables to control for seasonality. In the second part, I'm going to introduce Edstag model, which is a widely used model to analyze carried over effect of advertising. Then, I'm going to explain how to control for the carried over effect by using lagged variables in a regression model. In the last part, I'm going to introduce a study on TV ad effect on online search by Ju and his colleague. Fixed effects. In general, if a statistical model has only fixed model parameters, then the model is called a fixed effect model. Usually, a fixed effect model is used to analyze data with several groups that have different group means. Here is an example. The data are two-dimensional, having sales and price information for each breadth and width. A fixed effects model assumes that the mean or baseline sales varies across the brand. Here we have two subscripts, J and T. J denotes breadth and T denotes time. Then the baseline, denoted gamma, varies across the brands. That's why gamma has subscript J, meaning that gamma is J-specific, that is, brand-specific. What does that mean? For brand A, its baseline coefficient is gamma A. For brand B, its baseline coefficient is gamma B, which is different from gamma A. For brand C, its baseline coefficient is gamma C, which is different from gamma A and B. Across the brands, price effect is common, but each brand has its own mean or baseline level of its sales. For better understanding, let me show the details of the data structure. As I mentioned, the data are two-dimensional, brand and time. So each observation is associated with a unique brand time pair. That is, there are brands A, B, and C's sales and price data over the weeks in the data. And this table is the conceptual image we have about the data. But the actual data are stored differently from the two-dimensional image. The data set is actually unidimensional, and let's say this dimension is observation dimension denoted subscript I. Instead, each observation contains information of the two dimensions. For example, observation 1 has the data of brand equal to A and time equal to June 6, 2005. That is, we have the following correspondence. On observation, I is corresponding to a unique brand time pair, J and T. The brand and time variables give us which brand and time the observation is associated with. So, we rewrite the fixed effect model as the model of a unidimensional dataset. Each brand time pair is simply replaced with each observation, and the brand subscript is replaced with the brand variable. Now, this gamma is a function of the brand variable. That is, the value of gamma depends on the brand variable. Using dummy variables is a smart way to operationalize this redimensioning. The key of the redimensioning is how to operationalize this gamma function that depends on the brand variable. Mathematically, this function is exactly the same as this formula. Here, this I denotes an indicator function, so if the input of an indicator is true, the indicator has 1 as its value. If not, it has 0 as its value. And a variable created by this indicator function with the condition is a dummy variable. For example, if I observation is associated with brand A, then only the first indicator becomes 1 and the others have 0. Gamma A times 1 plus gamma B times 0 plus gamma C times 0 equals gamma A. So we end up with having the correct baseline parameter for brand A. This is a snapshot where the dummy variables were created. For convenience, DA, DB, and DC are the dummy variables for brand A, B, and C respectively. Then, the fixed effect model is the same as this unidimensional regression model with dummy variables. Those gammas are the dummy variables coefficient to be estimated. But we have one more step. A regression model generally requires a common intercept for all observations. So, just do the math. This is the fixed effect model on the unidimensional space. For brand B and C, subtract gamma A from their coefficient and add gamma A to them again. This doesn't change anything. Rearranging the terms, we have all terms with gamma A, and here's the trick. Sum of all dummy variables is always equal to 1 because only one of them has 1 and others have 0 at every observation. So, finally we have this regression model with a common intercept. This common intercept captures the baseline. In this case, brand A's average is set to the baseline. And the coefficient of the dummy for brand B captures not brand B's average, but the deviation of brand B's average from the baseline. And the coefficient of the dummy for brand C captures the deviation of brand C's average from the baseline. Fortunately, R has a good function to execute this strategy. Its vector function in LM function creates dummy variables and adds the dummies into the regression. Left-hand side table is the result from the regression using S vector, and right-hand side table is the result using the dummy variable. As you can see, all results in the left-hand side are identical to those in the right-hand side. Then, why consideration of the fixed effects is important? Please recall the Mr. Mistake and Miss Perfect example. The brand effect was missing in Mr. Mistake's analysis, and adding the brand effect make a positive coefficient turn negative. That is a typical example of an omitted variable bias. Suppose the following true process, but the dummies were missing in the model estimated. Then B significantly deviates from its true value if the omitted dummies are highly correlated to the price variable. The left-hand side table is the regression summary with the brand dummies, and the top right table is the regression summary without any brand dummies, and the bottom right table is the correlation coefficient between the low price and the dummy for brand C. If dummies are omitted, we have positive price coefficient about 1.87, but this value is the sum of the correct price coefficient and bias, which are negative 1.09 of the price coefficient and about 3 of the bias. This big bias is coming from this very, very high correlation coefficient between the dummy and price. There are no exact formula to compute the omitted variable bias, but we can roughly expect the sign of bias based on the sign of the correlation and the sign of the omitted effect. Let me go back to the Mr. Mistake and Miss Perfect example. Brand C's price level is much lower than brand A and B's prices. The dummy for brand C has 1 if an observation is for C. That is, price goes down if dummy for brand C changes from 0 to 1, indicating a negative correlation. Although brand C was cheap, market share of brand C was not that high, mostly low. That is, the omitted brand effect for C is negative. As in the table, in this case, omitted effect is negative and the correlation between the omitted and remaining variables is negative. Thus, positive bias is expected, and we found the positive bias from the estimation in the previous slide. Then, what? Omitted variable bias can be viewed as a confounding effect. The brand effect is negative, and the brand is highly correlated to price. That is, the brand effect is also highly correlated to price, leading to the bias. Thus, the higher the correlation and the stronger the omitted effect, the bigger the bias. The concept of the fixed effect is useful to control for seasonality. Seasonality is defined as follows. An event is seasonal when it happens periodically, that is, at regular occurring intervals. For example, this is beer sales data across 9 different stores. There are many differences in the sales between the stores, but the overall trend is very, very similar, and several periodical events were found. In summer, beer sales periodically surge, like this point. Also, we found that beer sales surge too in Christmas season. There are various methods to model the seasonality. A group of methods is type series analysis, including ARIMA, HMM, wavelets, and etc. Those models rely on periodical patterns in historical data, like that something happened 12 months ago happens again. That is, those models focus on identifying the periodical interval 12 months from data. Another way is to use dummy variables. We can create dummy variables for all events that periodically happen prior to analysis. To control for the seasonality, we may put all of the dummies. And for each seasonal event, this approach focuses on the average effect size over time. This is the dataset of beer sales that were plotted in the previous slides. From the time information, we can extract the week number, and using as vector function, we have all of 52 week facts. Seasonality control is important because farms' decisions, like pricing, are sometimes highly correlated to seasons. These two figures show weekly trend of demand volume and average price for ready-to-eat canned soup. The green area indicates the off-season in summer, and as in figure 1, demand volume is relatively super low during the season. But as in figure 2, during the summer, the soups were sold at a relatively high price. Thus, if the seasonality is missing in analysis, we may have omitted variable bias due to the high correlation between the price and seasonality. Then, how to determine the seasonal granularity? There are no clear rules and no rule of thumbs. In general, if seasonality is coarse in analysis like monthly or quarterly dummies, interpretation of the seasonal effects is clear and straightforward. But the seasonal effects are highly likely to be smoothed out. That is, some important seasonal factors could be missing. For example, consider Black Friday week with monthly dummies. When we assume monthly dummies only, the Black Friday sales may be divided into November average and December average, which are captured by the monthly dummies. Of course, sales increase during the Black Friday season is reflected in November and December sales levels, but the peak sales and the peak price discount information during the Black Friday week is highly likely to be washed out. On the other hand, if seasonality is fine in analysis like daily or weekly dummies, we can fine-tune various seasonal effects. The Black Friday week is separated out from the other weeks, and we can exactly control for the Black Friday changes. But the fine-tuned seasonality also faces a problem. For each seasonal effect, like week 1 effect and week 2 effect, and etc., the number of observations could be too small, implying that there is a possibility to be confounded with outlier. Now, let me move on to the carryover effect. It sometimes takes a long time from an ad to a conversion. Once the consumer watches the ad, she may search the internet for more information about the product. She may consider other options instead of the product. And after that, she may purchase the product. This is just one possibility. Of course, there would be a person who purchased the product right after she watched the ad. And of course, there would be another person who don't purchase the product although she watched it on ad. Anyway, once consumers are exposed to an ad, its effect is usually long-lasting. Ad stock model is a widely used model to describe the long-lasting ad effects. The model assumes ad stock, which abstracts how responses to advertising build and decays over time. Exposure to an ad builds awareness in consumers' minds and influences their purchase decisions. The details for the model are as follows. This is the simplest form of ad stock models with a Koyck man. In an ad stock model, sales or demand are a function of ad stock and other variables. And the ad stock is a stock variable to keep ad efforts denoted AD over time. This stock is decaying over time because the awareness created by ad exposures will be higher if there have been recent exposures and lower if there have not been. Parameter lambda is the decay parameter that controls for how long the ad effects are lasting. Here is an example. Suppose that lambda is equal to 0.5, meaning that the ad stock decreases by half every time period if there were no ad spending. And from the first time period, suppose that there was a unit amount of ad spending at every 10 time period. The table shows how ad stock variable is evolving over time. At time 1, there were ads, and ad stock is generated. At time 2, the ad stock decreases by half because there was no ad. At time 3 and 4, the same thing happened. And at time 11, new ads were coming, and ad stock is regenerated, and it decays again. This figure shows how ad stock changes with different lambda values. The black curve is for 0.5 as in the table, and the red dashed curve is for 0.9 of lambda, and the green dotted curve is for 0.1 of lambda. If lambda is 0.1 or 0.5, the ad stock decays to almost zero within 10 time period. Whereas, if lambda is 0.9, the ad stock does not entirely decay within 10 time period, so it shows a long-run increasing trend. If the ad stock model is or successfully describes the truth, we must observe that, obviously, sales are related to current ad spending, and sales are related to lagged ad spending as well. So, most advertising studies assume the ad stocking mechanism directly or put the lagged advertising variables to measure the ad impact. In R, we can easily generate the lagged variables through lag function. The n value in the function says which lag will be returned. If n is equal to 1, the function returns the previous value. If n is equal to 2, the function returns the value at 2 time points before the current time period. This is a log-log demand model for advertising. Plus 1 translation in the log function of ad is necessary in advertising studies because zero ad spending is often observed. Just for explanation purpose, I put only 2 lagged variables into the regression, but the length of the lag could be much longer. And this is the estimation result. The details will be discussed in the next page. Here, I have replaced estimated values for the Greek letters. This is a local demand model, so the interpretation must be elasticity concept. That is, the coefficient estimates are elasticities, the percent changes of sales when the ad spending increases by 1%. So, the effect of 1% increase in ad spending on the current sales is 0.43% increase in sales. The effect on the next sales is 0.17% increase in sales. And the effect on the sales at 2 points after current sales is 0.07% increase in sales. Thus, to measure the entire effect of ad spending, all the effects over time must be accumulated. As we discussed, from an ad exposure to the final conversion, there would be multiple steps for consumer to do. Searching is one of the steps. Min-gyu Ju and his colleagues investigate whether and how TV ad expenditures influence online search behaviors. They collected and combined TV ads and consumer search databases for financial service products. There are two dependent variables used in analysis. One is the number of category searches, and the other is the relative share of brand keyword searches. Here, category searches indicate all such queries related to financial services. Those searches can be divided into two groups: generic keyword searches and brand keyword searches. Generic keyword searches are search queries not limited to a specific brand like credit and invest. Whereas brand keyword searches are search queries directly related to a specific brand like CT and Ameritrade. And the main independent variable is each brand's advertising expenditure. This table displays weekday and weekend summaries of search query volume and ad expenditure for each brand. CT is the top brand in terms of ad spending. To relate the ad expenditure to search queries, a variety of log models with fixed and lagged effects is used. These two equations are the main equations in the article. The first equation models the effect of ad expenditure, denoted NET, on the category search volume, denoted YT. Both A and Y are log metrics, and there are some control variables, denoted capital XT, including time-fixed effects. The second equation models the effect of ad expenditure for the case brand, denoted A, KT, on the case brand keyword search share, denoted ZKT. Again, both A and Z are log metrics, and there are control variables, denoted capital X, KT, including time-fixed effects. This figure shows the main finding. TV advertising have a small but positive effect on category search. Out of the 96 lag effects, 76 are positive and statistically significant, and none of them is proven to be negative. A 1% increase in category advertising expenditures lifts the number of search queries by about 0.5% per hour over a period of about 3 days. This non-immediate, sustained, subtle effect may indicate that category advertising acts as a reminder for search. This figure shows the effect of lagged brand advertising expenditures on the share of brand keyword queries. Overall, TV ads increase brand keyword choice. 16 of the first 18 lagged effects are positive and statistically significant. Compared to the category expansion effects of advertising, this effect is lasting much shorter. Then, how big are these effects? This figure shows elasticities by day and hour. On average, given a 1% increase in a brand's TV ad expenditures, the model predicts, on average, a 0.17% increase in its number of brand keyword search queries over the following 96 hours. The effect is the greatest in the morning and decreases throughout the day before rising again after 5 p.m. and throughout the evening. The effect is slightly higher on weekdays than on weekends. This figure displays the estimated seasonality of search query volume. The search volume rises rapidly between 6 and 10 a.m. and then becomes flat until about 10 p.m., both on weekdays and weekends. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.